Here we go. All right. Well, thank you everyone who's joined us now or also joining us for the recording. This is going to be the third part of a three-part series trying to explain DataFusion and the Apache era DataFusion query engine architecture. Part one, we talked about what a query engine was and why you might need one. And in part two, we talked a little bit about the logical planning and sort of how expressions and you go from query plans to actually executing them, along with expression evaluation. And in this talk, I'm going to talk about execution. In particular, sometimes that gets called physical planning. What I'll talk about is basically how the actual data flows through the plans and how you go from logical plan to an execution plan. Your host today is myself, Andrew Lamb. I've worked on databases for a while, especially on analytic sort of columnar databases. And so you get to see my mug one more time. So I'll just sort of explain what a query execution plan is. So this is the thing, and again, much like DataFusion is not sort of architected differently than other columnar engines or other database systems in general. Likewise, execution is the same thing. So this area is typically called the execution engine in some database systems, or the physical plans or execution plans. Like all those are kind of synonyms. Almost all database engines have this lower level layer that actually does the work, right? One layer figures out what to do, and then the next layer actually does the work. So DataFusion's features, just to give you some sense, you can often have like a checklist of things. So DataFusion's execution engine is async, so that means you can avoid blocking I/O. It doesn't have to make a system call and then block threads. So it has that built-in courtesy of Rust. We'll talk about that in a little bit more. It's also streaming. So depending on what you're familiar with, streaming means you don't have to read the entire input into memory in order to process it. And that of course doesn't apply to every single operation that you do, but a lot of operations, DataFusion will incrementally be able to process the data without having to buffer the whole thing. It's also vectorized. So if you'll hear buzzwords about different query engines, they'll also talk about streaming, vectorized, query engine, or whatever. So vectorized is just a fancy way of saying, because you're streaming, rather than streaming a single row through at a time, what you're actually doing is you're streaming record batches like we talked about last time, but those are sort of a bunch of rows at a time stored in a columnar fashion. So that means each one of the operations, even though, yes, it's streaming, right? It's streaming at the overall plan level. It's not individually, you're processing batches at a time. It's also partitioned. So partitioning partition is a word that gets overloaded in many systems because it's such a general term in the English language. In DataFusion's word, and again, we'll talk about this later, partition means that every sort of every operation that's doing something in the execution plan actually happens in parallel, and the number of parallel branches is controlled by the partitioning. So the execution engine can take advantage of the way the data is distributed around, and DataFusion uses a mechanism called partitioning to do that. Multi-core, it's multi-core in the sense that we use multiple threads, but it uses the Rust asynchronous runtimes to do this. So there's no explicit thread creation in DataFusion execution engine. Instead, it's all in terms of Rust tasks, Tokyo tasks, which then there's a scheduler that's built into the Tokyo framework, which is the synchronous I/O framework, which then maps those onto thread pools. I put in a star here because I would say there's still some unease about using the same implementation for the I/O and the CPU-bound tasks. There's both benefits to that and drawbacks to that, but that's how DataFusion works today. We use the same thread pool, same abstraction. It doesn't have to be the same thread pool, but it often is. All right, so how do you do execution planning? So I've heard some feedback that physical planning is confusing because we also use the term execution planning. So just to be clear, execution plans and physical planning are the same thing. It's kind of unfortunate that we use different terms, but they're talking about the same part of the process. So the way you go from a logical plan, like we talked about in part two of this series, to actually running and generating the results for your query is the DataFusion will create a execution plan. Right, execution plan is the name of the structure, the trait that's actually used for this purpose. For better or for worse, the function that actually turns a logical plan into an execution plan is called create physical plan, just to make things confusing. But this is the same thing, execution plan, physical plan, same thing. I'm going to try to use the term execution plan in the rest of the talk to keep things consistent. Once you have an execution plan that's not actually running yet, it's not actually generating record batches or doing work yet. Instead, you then need to call a separate function called execute on those execution plan. And each execute, and I'll describe how this works recursively too. Execute, you don't, you not only do you call execute, you have to give it a specific partition number. Like I said, every execution plan has some number of partitions that was decided by the planner based off whatever your the options you might have specified are. And you call execute on that execution plan for each one of the partitions, and it gives you back a stream. In particular, it gives you a stream of record batches. Again, that I'll talk about a little more in a second. And it's the implementation of those streams that's the thing that's actually doing the work, that's allocating the buffers and generating hash tables and running filters and doing kernel, running arrow kernels like we talked about last time. So this record batch stream is like that's where the actual computation is occurring. So this talk is going to talk about the execution plans and these record batch streams and how they get created. And once you have a record batch stream, you can then get record batches out of them depending on what you want to do. So if you're trying to send it over the network, for example, as part of Aeroflight or something, you would sort of probably, as the plan creates record batches, you'd send it over the network in a streaming fashion. Or if you're trying to write it to Parquet file, you can stream it into Parquet. If you need it all in memory for some other reason, you can actually sort of collect them all in memory as well, whatever you want. But this is the end. This is like where DataFusion ends and you get record batches out. So the first talk in the series, we talked about DataFusion, put data and a query in one end, you get record batches out. Like here, we finally got to the record batches coming out the other end. All right, so let's talk about what Sendable record batch stream is. So this is a name of I think it's actually a type def, possibly it's a trait, I can't remember exactly. But what it is it's what you get when you execute one of these execution plans. And in particular, it's an async stream. So Rust, has a notion of async built into the language, which is a language construct that generates continuations for you. If you don't know what that means, that's fine. What it means is that the language itself has a way to stream and sort of return control when you're waiting for more work. So rather than have our own API or abstraction layer for doing that inside DataFusion, it uses the Rust asynchronous stream as something it's not actually, I don't know if it's built into the Rust language, but there's a standard stream interface that gets used. I think it's in the futures crate. So that way we can reuse all the Tokyo machinery and all the standard Rust library and compiler support. What you actually get out of these record batch streams, you don't actually get a result of record batches, or you don't actually get just record batches, you actually get a result, right? So that's the Rust way of saying that's how you return errors through here too, right? So you get a stream of record batches, you might also generate an error during execution, and that's would show up as next time you pull the stream for the next output, it will produce a result. The other thing about a Sendable record batch stream is that it produces a schema, right? So you can actually know before you generate any data at all what the shape of the data that's coming is. The way you use one of these in very stylized Rust, just to try to make it even more explicit, is you would have this execution plan that we're going to talk a lot more about how to get one of these in a second. You then call execute on it like I've been describing, right? And there's a function called await, well, it's not a function, this is a keyword in the Rust language. This says to run something that's asynchronous. So this will actually go launch the plan and begin the stream running. And then when you're ready, you get the stream out that you don't have any results yet. Instead, what you have to do is you have to sit there and poll the stream. So in this case, I've shown you it works kind of like an iterator. You have the stream, you say, I want the next record batch. You then call await the Rust compiler here. If there's no record batch available, we'll actually return control to the task scheduling system and something else can use that core. But if when the next record batch is available, your code will return here and things will carry on. So that's how you use them at like the highest level. So what you might get out of doing something like this is maybe you get a record batch with 4,000 rows, maybe then you get one with approximately 4,000 rows, and you get some more, and then maybe you get a small one. So these aren't meant to be exact numbers. I'm trying to illustrate here, as you get the stream of record batches, there's no guarantee that they're all going to be the same size. There's a setting that you tell DataFusion that you sort of would like the size to be approximately. It's called the target record batch size, I believe. But there's no guarantee. So you're going to get a stream of record batches. They're all approximately the same size, hopefully, but there can be significant variation. And then, of course, you get the end of the stream. All right, so that's like the core thing. You pull record batches off the stream. All right, so let's now talk about how that feeds into partitions, like I was talking about. Every execution plan, as I mentioned, does the same calculation, but it does it potentially in parallel on some number of these partitions. And the partitions are what represent distinct streams of value. So if you're more of a visual person like I am, I'll try to illustrate this with a diagram. So in this case, I have a filter exec, which is an execution plan, which evaluates a filter, kind of like we talked about last time, where it evaluates an expression and produces output where the expression evaluated to true. So in this case, I'm going to show inputs coming from the bottom, outputs going through the top, consistent with the discussion last time of like data flow graphs where the data is flowing from the bottom through the top. And so let's say this filter exec had 4 partitions. In this case, I'm trying to say partition 1 would when you actually called execute would give you something like this, right? It'd give you it would happen to be a filter exec stream, and you would feed it record batches in and it would produce record batches out. But to fully execute this plan, you actually need to call execute on each one of the four partitions that this had. So this actually, when it goes to run, there'll be 4 distinct filter exec stream instances, and each one will be pulling different record batch, like a distinct record batch stream. That's why I'm trying to make the pictures down here look different sizes, not because there's any meaning to the specific sizes, but the point is they're different record batch streams going through different instances of the filter exec stream that all, are computing the same logical result, or the same result that's called for by this filter exec, but it's doing it potentially in parallel. And again, it's not like we explicitly made 4 threads for this. There's a thread pool system that will run whichever one's available given the number of threads or available tasks. All right. So now I'm going to move up to this physical planning phase. Again, I'm sorry for the term physical planning. What that means is you start with the logical plan and you end up with an execution plan. So the logical plan, this is the same one as from our example last time. It's scanning a table, right? In this case, whatever this HTTP API request total table is, it's then applying this filter. Data should flow through here, and then there's an aggregate. So this is what the plan was, right? There's no data actually flowing through here. It just represents what you want. And then what will happen is there'll be a corresponding execution plan that gets created through a process I'm going to talk a little bit more about. So in this case, maybe the table was actually backed by Parquet. So this table scan doesn't actually say anything about Parquet yet. It actually just has sort of an API provider. By the time it gets to be an execution plan, it actually has a specific implementation of execution plan. In this case, Parquet is I'm illustrating. Then there's a filter exec that matches this filter node in the logical plan pretty directly. Then there's something a little more sophisticated. There's actually 2, there's 3 more nodes that the single aggregate in the logical plan actually turned into several execution plan nodes. And in this case, this is representing a multi-stage group by. I'm not going to explain too much about that, but this is one of the ways you can implement grouping very quickly in parallel. Not the only way, but it's one way. It's a classic way, and it's what DataFusion does. So what this strategy means is that as you go and read your file, you can do an initial aggregation on the output of each stream. So in this case, let's say you have 2 files and you're reading each one as an individual partition. Since we're computing the counts across whatever this was, counts across the status, you don't have to put them all together and do one count. You can actually compute partial counts for each file, and then you can combine the partial counts together in a final mode. So that's the structure that's encoded here. So you do this initial pass. This strategy, by the way, is very effective for low cardinality grouping. And then you put it all together and you do the final group by at the end. And you can already see there's like some hints here, right? Where you're going to combine a bunch of partial counts from different files together, right? You actually don't count the counts, you sum the counts. Again, that's not like rocket science, but this is one of these details where to get all this stuff working right, you just have to think about it and get it working. So DataFusion does that for you. So now we have an execution plan. That's this blue stuff. And now I'm going to show when you actually call execute on that, what happens. And in particular, I'm going to try to pictorially show the streams that come out of it to give you a sense of like what actually at runtime is going on. And then we're going to try to walk through as much as we can what actually is happening. So in this case, there's an execution plan. I've annotated it with the number of partitions. This is some property that's on the actual execution plan itself. All right, so in this case, there's 2 partitions for this one, 2 partitions. Then there's only 1 for this coalesce partitions exact thing. And then there's a hash aggregate, which only has one partition. So I'll do it from the top down. You would call, let's say this is the top of the plan, right? So the final output plan from DataFusion will typically have one partition, or you can make it have one partition. Someone calls execute on that, and then recursively, the way these execution plans work is they'll call execute on all their individual input partitions and then connect them up with whatever stream they're supposed to. So in this case, the hash aggregate stream will be created. It will then connect it by calling execute on its input. Coalesce stream actually its input has two partitions, so it knows it needs to call execute on both its left and its right input, or on its partition 0 and partition 1. So it'll call execute on partition 0, which will make streams for each one of these individual execution plans. Then it'll also call execute again because it knew it had two partitions. So that means there's going to be a second copy of these, and the same thing will happen. So you now, each one of these is computing the results for a partition, and that's now you can see, like, this looked like a linear thing. It's actually now a tree with a bunch of distinct operations. Each one of these streams implements sendable record batch stream, and so it implements that interface. And so this coalesce stream has no idea it's actually above a grouped hash aggregate stream. It just knows it has a sendable record batch stream that it can pull data from. So all these are pretty general purpose, and you can make whatever structures down here you need for your plans. All right, so we have this red thing and it's ready to rock. Like, this is the actual thing that's going to go compute all the results. So what I'm going to try to do now, and I've tried to do this several times, I don't expect that you'll necessarily get it all. I'm sorry, I'm not gonna probably do as much. I'd love to do it better justice, but I'm going to do the best I can. So what I'm going to try to do now is I'm going to try to explain the sequence of steps that actually happens as this executes. And it's going to be complicated by the fact that there's asynchronous stuff involved, and it's some combination of push and pull, right? So a classic push-based scheduler would compute data here and then try to push it all the way up. Classic pull-based scheduler would start here and sort of call all the way down and just try to pull data back up from the plan when it was ready. And DataFusion has a combination, some combination of those two classic strategies. So it gets a little wild. But anyway, so what I'm going to do is I'm going to explain how this part of the plan works, and then I'm going to explain how the top part of the plan works in two different slide builds, and hopefully that will give you some flavor of what's going on down here. And again, like, unless you are going to be implementing one of these streams, you don't have to necessarily understand all the details. But what's, I think, interesting to know is, like, there's an awful lot of sort of thought that's gone into this model. And if you want to work at this lower level, you do need to be aware. So it's ready to go. So this part of the plan, right? Remember, this is just this part of the input right here. We're going to start. The way you start a stream is you call next on it, right? You call this next function. You actually call poll next, at a lower level. Let's just say you call next. So the first thing, as soon as this gets called next on it, the first thing it does is actually it spawns a new task. So because this hash aggregate needs to build a hash table before it can produce one of its outputs, it's what's called a blocking or a pipeline breaking operator, which is different than filter or parquet or something. So basically, in order to avoid the delay of starting to compute the group by table, as soon as you start this running, it actually spawns a task and immediately starts pulling data from here. Even if the output isn't necessarily ready, it's going to try to eagerly consume all of its input to build that hash table so that it is ready when someone calls. So the first thing is that then, to compute the output grouping, you need to get the input. So the way it gets input is it effectively calls next on the input to it, right? So it filter exec is its input. Filter, like, what, I can't filter anything until it has input. So it also calls input next on its input. The parquet stream is the thing that actually is connected to the Arrow RS parquet reader that we've written about. But eventually that will produce a record batch at some point, right? Maybe it has to go fetch data off object store, maybe it does some other stuff, but eventually it produces a record batch. And now it's ready to pass that back. Now I'm showing this as kind of like a series of function calls, but it's actually these await asynchronous tasks, async calls that are built into Rust. And so even though this looks like a function call await, it actually returned control back to the thread, the thread pool. And so other stuff could have been happening, for example, while we're waiting for Parquet data to come back from the object store or something. So that, but eventually it does get a record batch and it returns control back to filter exec when it called. Filter exec does the filtering that was requested. So it calls the appropriate arrow kernels like we talked about last time, and will just pass the rows on that match the predicate. That will then get passed to the group aggregate stream, right? Because it called next a while ago, but the results are finally ready. And when the results are ready, what the group hash aggregate stream does is that that's the thing that actually has a hash table. If you're familiar with computing grouping, group by hash is you basically keep a hash table for each one of the distinct groups, and then the value in the hash table is the ongoing aggregate. So like in this case, the count. So in this case, the group hash aggregate stream has all the code to build that hash table, find the appropriate entries to update based off the contents of the record batch. And it's, and this process will repeat as long as there's data coming into the stream. And as soon as the stream into the group hash aggregate is done, then it knows enough that, all right, now it's finally ready to produce its own output. That's what the group by hash aggregate streams algorithm is. Once it's received all its input, then it can produce output now. And now in this case, it'll start producing record batches out of the hash table and passing them up to whoever, remember we started this whole process because someone asked, some consumer asked for data from the group by hash aggregate. Yeah. So now I'm trying to show too, perhaps this output was not requested yet, or maybe it actually was requested immediately. Either way, the asynchronous machinery down here is going to run until this record batch is ready. But I'm just trying to show that this request might not come here initially. That might not, that's not what necessarily kicks off this run. That this stuff starts immediately when you call execute. And then step 6, obviously you give the record batch stream back to the caller. And again, it's not just a single record batch necessarily, it'll generate the output in chunks, even though it's actually coming in this case from the same hash table. It's the group hash aggregate stream is clever enough to know to generate the output in pieces. So now we're going to switch, well, who was asking for the output? Well, if you recall, this is now the top half of the plan I showed earlier. And so this is the top half, and I'm going to try to explain what's going on up there. Again, I'm sorry if you've lost here, but this is trying to give you the sense of this I would say it's fairly sophisticated what's going on. The coalesce stream likewise has this eager property that I was trying to describe, where it doesn't actually wait for someone to ask, it doesn't wait for its consumer to ask for the first record batch before it starts computing its own inputs. And so it basically spawns tasks immediately to try to pull data out of the two inputs. In this case, it's the two group by hash aggregate streams, which were, that's what I was trying to show in this part. So immediately they start getting pulled, and they, now it's waiting. And let's say in this case, the output is requested because this is the final output of the query. And so someone wants to know what are the query results. So at some point in the future, the record batch streams, so the record batch from the previous slide is going to be ready, because the first phase, you've read all the data out of the Parquet files, you produced these two hash tables right in parallel of partial results. You then, as those streams comes through, they get passed up the plan. So in this case, the coalesce stream, all coalesce stream does is takes two partitions and just interleaves how the record batches as they come in whatever order. Eventually, the new stream of partial aggregates encoded in record batches gets fed to this other group by hash aggregate stream. It's the same actually operator, just with some different aggregates functions specified. So just like before, it feeds data into the hash table, right? It's a different hash table than was on the previous slides, but it is the same code that's running, which is kind of neat. And then eventually, just as before, when it's exhausted all of its input, it knows how to produce the output. And this output, this record batch, this is the final output of the query, and that's eventually returned back to the caller. So that's there it is. I don't know how to make this any simpler. It's not simple, but I'm hoping this at least gives you a flavor of what's going on when you're actually running a plan. Right, so there's a fairly sophisticated data flow graph happening down here, and there were obviously a bunch of steps that needed to get to this plan. So let me take a step back now, and for the next couple of minutes, I'll just talk a little bit more about what the options for execution plans are, what DataFusion has built in, and how like some of the other things that happen. So DataFusion has a whole bunch of execution plan nodes here. You've seen several of them because I've just been showing them to you, like filter exec and aggregate exec. And it's also got ones to do limits. It has a sorts, right? Sort preserving merge is if you want to maintain a bunch of partitions but keep their sortedness, there's a way to do that. You can see here there's several different two different ways of doing window aggregates depending on the properties of the input, right? Because they actually use different algorithms. There's something that sticks partitions together. There's a selection of built-in execution plans that know how to read various different data sources, right? So there's one for Avro and one for these different formats that then use sometimes the arrow reader, sometimes another reader to actually do the work. There's ways to provide data in memory. Maybe there's ones that don't actually produce any rows. There's also, this is a, if you have your own file formats that you want to stick to DataFusion, you have to provide your own implementation of execution plan, which is fairly straightforward. I'll show an example of it in a second. Then there's various execution plans that let you reorder that reorder the streams and partitions in various ways. Like repartition exec can spread the plan out or reset it into new partitions. Coalesce partitions does the opposite. It brings multiple partitions back into one. Coalesce batches is typically run after a filter node so that instead of like a bunch of little tiny record batches, right, because filtering might very well filter out lots of rows, it'll try to make sure that the record batches that get passed on to the rest of the plan are still a sufficient size to amortize the overhead of record batches. There's then the classic selection of joins. Actually, DataFusion's join support has gotten much better in the last, I would say, year, thanks to a lot of work from some key contributors. But now it has a significant selection of join algorithms, and which one it will use depends on some of the properties of the input streams. But we've got like the hash join exec. This is like the classic one everyone has. But then there's a variety of other execution plans for depending on other properties of whatever the query is trying to compute. Something else that's very important is the sort order. This is something that the execution plan knows about and communicates to the optimizer, which I'll talk about in a second, communicates to the rest of DataFusion using the execution plan trait. But then there's a variety of optimizers in the DataFusion execution plan regime, physical optimizers they're called, that can take advantage of the sort order. So this is important for things like window functions, where to correctly compute a window function, you need to make sure that the data for the window is next to each other in the stream, right? Which you do typically with sorting. It also allows other data sources to provide information like, if the data is if you have files that are already sorted, you can communicate that to DataFusion, and then DataFusion will like not resort it if it doesn't need to, even if like the upstream thing, like a window operator needs to have the data sorted, you can do that. Sort order, I assume you all know what sort order is, but maybe it's worth a brief example. So in this case, the data is sorted by B and A, right? So that means if I have two columns of data, it's first sorted on B, right? So this is sorted ascending on B, right? Every row is getting bigger, and in rows that are tied, we'll look at the value A. And so for rows in B that have the same value, the rows will be sorted in A ascending, right? So you can communicate this type of sortedness to the DataFusion optimizer, and it takes advantage of it. Yeah, so here's an example. If the query asks for data to be sorted by B then A, it's not going to bother to resort it. And for large data sets, that might actually be a pretty significant win. I think the most important built-in optimization is for these window functions. Why sort order is really important, but there's other things, other reasons as well. Like joins, for example. If you want to do a merge join, it has to be sorted correctly. All right, here is a brief copy-paste version of what's in the execution plan trait. So execution plan, this means like the source code. If you go look at the execution plan, this is the interface that each one of those plans that execution plan nodes I just described provides to DataFusion. And so you can see some of the concepts I've been talking about. Like it knows what the output schema is. It knows what its output partitioning is, right? How many output streams it's going to make. It can say whether or not it's going to be, infinite, whether it's ever going to actually end. What's its output ordering? Some of them actually have specific requirements for input distribution or input ordering that it can describe, and rather than have, and this, if the DataFusion optimizer passes will ensure that this is maintained. Yeah, does it actually keep the same input order? And some other stuff here too. What are the children? Whether it would be valuable to run it in parallel. Tell me something about the runtime mount counters. If you ever do explain analyze, if you remember that from the first talk we did, the original source of the data for explain analyze is these metrics that are reported from the execution plan. Here's the thing that actually runs it and turns it into a stream, right? That'll actually run. You give it the partition, and it gets a sendable record by stream, and it has some way to get output of statistics too. Just like we're running out of time here, but just like in the logical optimizer, there's in the logical level where you have logical plans and the logical optimizers where there's a logical where there's several passes. The same thing happens in the physical optimizer. So the execution level optimizers. So in this case, you get a single execution plan as input, and then we've run it through several optimizer passes that generate hopefully the same output, right? Should generate the same output, but hopefully do it faster or better or something. And so the examples that I have built in here these probably should be called something different than optimizers, but right now they're in the optimizer framework. So that's just how it works. There's something which goes and makes sure that the sorting and partitioning that's described by the execution plan trait I just showed you is actually enforced. So if an operator says I need my data sorted such and such a way when it's coming in, like a merge join would, these passes will then go make sure if it's not sorted that way, it'll actually stick sorts in there to make it do that. And likewise, it'll make sure that partitioning and sorting is correctly done. Then there's also a sequence of passes that goes and tries to pick the best algorithms. So joins, I just showed there's like 5 different join algorithms that you can use in various circumstances. So there's a pass that tries to pick the right one there. There's something that tries to do whether or not you need to exactly which type of sort you need. There's something which tries to avoid adding pipeline blockers if possible. And then there's a couple of passes that use statistics to try to avoid reading data if you can. So like, for example, if your query, very common is like select count star from the file, right? Because I want to know how many rows are in the file. You don't actually ever have to read the file, read any data out of that file to compute that result. You can do it simply with statistics. So that's what that pass does. And also certain file formats like Parquet, right, have access to the minimum and maximum as well. So if you know the minimum value in your Parquet file, you don't have to look at the values at all. You can literally just use the metadata and do that. And so that happens in the physical optimizer pass. All right, so that, I think I did better on time this time, but I'm still over. Thank you very much for listening. Here is a very, I think, active community working on DataFusion and Arrow, and here's some links to come get involved. We'd love to have you be part. And yeah, thank you all very much. See ya online.